Okay, I started recording. Yeah, looks like I'm not taking notes today. I guess I'll do the voting part stuff.
Nicholas, any questions?
Yeah. Are we getting back to midterms today?
No. No, not today. Unfortunately. Or fortunately, I don't know.
Wait, based on how much you have created, how are you midterms?
I will discuss that at a later time once we get them back. All right, so good morning, everyone. We will pick up from where we left off last day. Now, today we're going to say a few more things about the Biot-Savart law and then jump into Ampere's law and Lorentz force. Did you have a question?
Yeah, I was going to ask about the midterms.
Yeah, so midterms will be back next week. Okay, so they're not graded yet. Yeah, John?
Just to make sure, is this working properly?
Sure. Yeah.
Want to check on
Press
it?
the record button.
Yeah.
Good.
Does it look like?
Yeah. Red light.
Yep.
All right, so. Yeah, so we are going to finish off with the Biot-Savart law today. But we're not going to spend too much time on the Biot-Savart law because we want to move right along to Ampere's law. And Ampere's law will give us a simpler way to calculate the magnetic field. Kind of like how Gauss's law gave us a simpler way to calculate electric field. Okay, so you'll remember, let's just review then the Biot-Savart law. So, said that a moving charge, so charge Q that's moving with speed v creates a magnetic field. And that magnetic field is always perpendicular to from the velocity vector to the point of magnetic field that you're interested in. Okay, so we drew a picture last day of a charge Q moving with speed v and finding the magnetic field at that point. So here's our R vector, which points from the charge to the point that you're interested in. And then R hat is just a unit vector that points from the positive charge to the point that you're interested in. Okay, so this is a vector equation because magnetic field is a vector. If I want to look at just the magnitude, we also wrote down the magnitude for a point charge, mu naught over 4 pi q v sine theta over r squared, where theta is the angle between r hat and v. Okay, so this is nothing new. This is what we looked at last day. Now, some interesting things about this law. So it depends on v, right? If v is 0, there's no magnetic field. And also there's a 2 on the denominator here, which means if I'm twice as far away, the magnetic field strength is 4 times less. It's an exactly 2. So this would be a law of physics that was discovered, and so one thing interesting about this law in particular is it only works for steady currents. That is, currents that aren't accelerating, which will be what we look at in this class. And what I mean by that is, what I mean by steady currents is the velocity is constant. So the charge is not speeding up or slowing down. In the case where the charge is speeding up or slowing down, so this works for V constant. That means acceleration is equal to 0. If you have charge that's accelerating, there are more general equations called Jeff-Menko's equations, which allow you to find the magnetic field. But we won't concern ourselves with that here. So V is constant. And now let's look at some other ways of expressing this law, because this basically tells me the magnetic field for a point charge. Okay. Now, just to check our understanding here, let's just try an example. Let's take out your voting cards. So a positive charge is moving straight out of the page. What is the direction of the magnetic field at the point? Give you a moment to prepare your vote. And let's take a vote. 3, 2, 1. Correct. So most of you are saying B, which is correct. The magnetic field is down. If I point my thumb here in the direction that the charge is moving, where at the point of the magnetic field, it would point down. Okay. Now, using the Biot-Savart law, we could say the magnetic field B is given by the cross product of V cross R. So in fact, just using the right-hand rule for the Biot-Savart law, what I would do is I point my fingers in the direction that the charge is moving out, and then I could curl my fingers in the direction of the r hat vector, which would be this way. So I get a downward magnetic field at this point. Okay. Now, if this point was translated out of the screen this way, the magnetic field would still point down. It would just be a weaker strength. So the magnetic field always has to be perpendicular to the plane of V and R. That's what the cross product guarantees. B is always perpendicular to V and R. And then these factors here, well, this factor here is really what determines the strength. And the angle between them determines the strength as well. Question?
So on the board, the velocity going to the right, is that supposed to be coming out of the board, the magnetic field?
So, yes. So if I go V cross R, I would get a magnetic field at V that points out. So in fact, the magnetic field at this point would be out of the board. So in practice, the right-hand rule, this is a vector equation, and it just tells us the direction of the field. To actually do a calculation, we'd want to use just the magnitude, and then use the right-hand rule to determine the direction. So this is what's true for a point charge, but if I have lots of charges, like a bunch of current, like a bunch of charges all moving together in a line, we call that a linear current. Well, then I basically am now doing an integral. Right? I'm doing this equation, I'm finding the magnetic field, doing a little piece, and adding all those pieces up to get the total field. So I wrote last day that something similar to QV. And by the way, QV has units of, well, what? Unit charge times speed. So if I'm dealing with more than one charge that's moving, I might want to express Q times V in another way. So one way that we saw was, I might write it as I dl. So current I is equal to dq dt. This is the linear current. Well, I we're familiar with as just being our normal linear current. Now, if we look at the units here, current is the time derivative of charge per unit time, how much charge is passing a point in the wire per unit time. If I multiply that by length, I have charge per second. Multiplied by length, I have a charge times speed. So of course, if I rewrite it using a different expression, it also has to have charge, have units charge times speed. It's IDL. Now, let's say I'm dealing with not a linear current, like a really thin wire. Let's say I'm dealing with a surface current. So K is surface current density, and K is equal to I, or is equal to current per unit length. I'm actually going to put this up for a minute. So this is surface current. Whereas I is our normal linear current. Now what's an example of where you might have surface current? What kind of material? Conductor, right? Because all the current that charges that flow on a conductor flows on the surface when the conductor is in equilibrium. Now, let's say we have a non-equilibrium conductor, like a wire. Well, there we have this quantity that we've already seen when we were studying current, and that was current density. So current density, J, multiplied by d tau, which is a small volume element. So J is just current per unit cross-sectional area. So it measures the amount of current that flows through a particular enclosed area. This is current density. So typically, well, that's basically all the substitutions you could do into the Biot-Savart law. And then to find the total magnetic field, you would basically take these little chunks, for instance an IDL, and just add them up into a big chunk. Question?
Should the units, why are the units for K not current per area? Why is it current per length?
Because if I have, imagine I have a sheet of current, for example. A sheet of current. And now we've really just had so far a line of current, right? Let's imagine that this sheet of current has length, cross-sectional length L, and there's a current flowing through the sheet like this. Now K is what describes that surface current. So if I want to know how much current, if I want to have a charge times speed, here I have a charge per unit area. So I have charge over meter squared multiplied, or sorry, charge per unit length per unit time multiplied by square meters, and I get a charge times speed. Because it measures, if I multiply it by dA, it measures a flow rate, charge times speed. Right, now, the basic charge configurations that we have, right, when we look at magnetic fields is either a long line, like a current. The current could be this long, or it could be really, really long. Right, or a bunch of loops of charge. And a bunch of loops of charge, if you stack them together, you get a solenoid. That's what we looked at last day. Okay, so in practice, the Biot-Savart law is rather difficult to actually use. So we're going to use, you'll have a couple examples in your homework of applying the Biot-Savart law. And then we're also going to look at Ampere's law. Ampere's law will give us another way to calculate the magnetic field, but in a way that's more simple. Okay, so before I get to Ampere's law, let me talk for a moment about line integrals, because we'll need to use line integrals in order to actually use Ampere's law. So just a recap here, because Coulomb's law we first used and we summed it up to a bunch of little chunks of charge, added them all up to get the total electric field. That was kind of difficult, so then eventually we moved over to Gauss's law. And for charge distributions with a high degree of symmetry, that allowed us to find the electric field in a simpler way. Gauss's law did. Now similarly, Biot-Savart law, those integrals to set up can be rather complicated. We did an example last day for a long wire, and we wrote down the integral by breaking it into pieces. And you could also have a loop of current as well. Those are the basic charge configurations, or current configurations, I should say, for magnetic field that have high degrees of symmetry, loops and wires, straight wires. But they're kind of hard to, any more complicated configuration would be rather difficult to solve using the Biot-Savart law. So in practice, what we're going to do is we're going to use the Ampere's law for current configurations that have a high degree of symmetry and use that to calculate the magnetic field. And that'll make the calculation much easier. So Ampere's law is to Biot-Savart law as Gauss's law is to Coulomb's law. This is the magnetic sort of equivalent. So before we can first of all discuss Ampere's law, I need to give a quick overview of line integrals. So raise your hand if you're familiar with line integrals. All right, so we just need to know the basics of line integrals. And the basic idea is, let's say I have 2 points in space, initial and final, and I have some path, P, between those 2 points, I and F. Let's imagine that you want to actually calculate the length of that line. And that line is a curve that's parameterized in 3 space. So it starts with a certain xyz coordinate and ends with another xyz coordinate. Well, if you were just measuring it experimentally, what you would do is you would take a little piece of string, right? And you would snake the string along that line. And then once you have pinched the 2 ends, you would just pull it straight and measure it. That's experimentally speaking, that's how you would actually measure it, right? Now, so calculus, line integrals will allow us to do the same thing. If I want to find the length, so I want to find the length L of this string here, I want to break it up into little pieces. And let me say that each piece has a length ds. So basically, if I add up a bunch of little ds vectors, I get the total length. So the total length is going to be the integral of ds. I just basically add up all of these little pieces. So this would be actually how we find the length of that line. Now you'd have to parameterize ds in terms of your coordinate system in order to actually do this integral, but that's something you'll do in calculus, or you've already done in calculus. So let's imagine now how we actually do a line integral is imagine that on this path we actually have a vector field. Let's say I have a vector field. So here's my vector field, and it's a diverging vector field to the right, and I'll say this is a V field. It's diverging as I go this direction, so this is what it looks like here. Now we could say at each point along the path, for instance at this point, there's going to be a value for the magnetic field at each point along the path. So what a line integral does is we're basically summing up all the magnetic fields. Let me call this little piece element I. So I'm going to sum up over I the magnetic field at I. And I'm going to dot that into ds. Okay, now I've already written ds here because that interval is really, really small. So if I take b and I dot it into something really small and I add them all up, that becomes a line integral. So this is equal to the integral of b. The I goes away because I got rid of the sum. B ds, well, b ds cosine of theta, where theta is the angle between b and s. So some simple cases for line integrals. If you look at some simple cases. Well, the first simplest case would be when b, well, simplest case would be when b is uniform, for example. So this is going to equal 0 when b is perpendicular to s everywhere. Then every little element gives me 0. I add up a bunch of zeros, I get 0. Line integral would be 0 if your magnetic field is perpendicular to your line element at every point along the line. You'd also have a 0 value for your line integral if, well, not a 0 value, but a simple calculation here would be just b times L. And in fact, this is what most of our line integrals wind up looking like when we apply Ampere's law, just b times L. This is going to be when b is parallel. When b is parallel s everywhere. Right? If b is parallel to L everywhere and it's uniform, I just take it outside of the integral. Cosine of 0 is 1. I'm just integrating over ds. So I'm just getting L, the length of that line. So in practice, when we apply it, I'm going to get to Ampere's law now, but in practice, when we apply Ampere's law, it's mostly going to be for line integrals. Well, the value of using the law will be for line integrals that are very, very simple, not complicated line integrals that your magnetic field is constant, it's parallel to the path, you just take it outside the integral, and then you just need to know the path length. Okay, so you probably do much more complicated path integrals in your calculus course. All right, so what is Ampere's law? Let's look at that now. Ampere's law is similar to Biot-Savart law, but it's actually, in fact, more general. And the reason it's more general is because it actually applies to magnetic fields. It applies to magnetic fields or for charge distributions that are not constant or steady. So the charge could be speeding up or slowing down. And Ampere's law would be valid for such cases. Yes, Thomas?
Just a quick question. What are we solving for there?
Oh, the line integral. So if I call this the line integral, the line integral equals 0 in this case and BL in this case. Or this is the line integral here. Now this works in many other cases. Right here for our purposes we're only going to look at line integrals for magnetic fields. But in calculus you look at line integrals for any vector field along any path. The application in physics is it turns out to be really important. Line integrals of magnetic field turn out to be really important when you're dealing with magnetic fields. This is a practical application of line integrals. Yes?
And what are the units?
The units of, the units here would just be magnetic field times length. So this would just be Tesla meter. Would be the units of a line integral. Yes?
Well, doesn't it come out to be work? Right? With this? Like if your path is from I to F on there and dotted with your vector field, won't the units of that end up being work?
So here's another physics application of a line integral, which is work, right? So line integrals also appear when we talk about work. So work is the integral of f dot ds. And work is a line integral. Now work is a transfer of energy. It has units of joules, but magnetic field doesn't have units of newtons. So when I take this integral right here, it doesn't have units of joules. Magnetic field is an interesting vector field. When we do the line integral of an electric field, it actually, around a closed loop, it gave us zero. That's why we were able to find the fact that the electric field, you can write in terms of a scalar potential. That's what we call an electric potential energy, right? Or an electric potential, so U and V, because the line integral around a closed path for an electric field equals 0. That's why that's why we could define the electric field was a conservative field. The line integral around a closed path was 0. The magnetic field has a very different property. Its line integral around a closed path is not equal to 0. And that's one of the big differences between electric field and magnetic field. And we already can see that because picture the magnetic field due to a wire. It just loops around and around the wire, right? So if I do a circular path around a wire, the magnetic field is parallel to that path all the way along the wire. So I take the line integral around the path, I don't get 0. And that's exactly the statement that Ampere's law, when we write it up here, will encapsulate. All right, good question. Now, any other questions? Okay, so Ampere's law basically says that let's just calculate. Let's imagine I have a current going into the board. So long, straight current. And what I want to do is I just want to calculate the line integral for a long, straight current. So this is a current that's going into the board. Now, does the magnetic field due to this current go clockwise or counterclockwise? Clockwise. So I'm going to choose a path that moves around clockwise. So my path, which I'm going to call an Amperian loop. It's, instead of a Gaussian surface, I'm going to create a loop, an Amperian loop. And that loop, we want to generally pick that loop to move in the direction we expect the magnetic field to be going. That's why I choose a magnetic field to go in the clockwise direction, because current is into the board and the magnetic field wraps around in this direction. So let's just calculate the line integral for this configuration. Let's just calculate B dot ds. So the line integral is going to equal the integral of B dot ds. Now, what we know as I go around this path, every point along the loop, the magnetic field is parallel to that little length element. And we already know the magnetic field due to a long straight wire. If this loop has radius small r, the magnetic field due to a wire is mu naught I over 2 pi r. So let's just plug that into this equation. Now B and B and ds are parallel. So this is just going to equal the integral of B ds, because the cosine of 0 is 1. I get rid of the dot product. Now, the other thing that I can do here is everywhere along this path, b is constant. So I can take it outside the integral. Right? That loop has a constant radius, so as I integrate around the loop, I can just take the b outside the integral, and what I get is b, the integral of ds. And ds is just the length of the circle. What's the length of the circle? Circumference of it, right? 2 pi r. And b is mu naught I over 2 pi r. And then I'm multiplying by 2 pi r. So what happens? The 2 pi r cancels out and I just get mu naught I. So this is an interesting result. The line integral around that current is only equal to mu naught times the amount of current that is through the loop. Okay. All right. Now let's generalize this result a little bit, and then we'll have Ampere's law. So let's imagine that instead of a simple circle like this, I make the Amperian loop a little bit more complicated. So I say, all right, well, I'm going to extend it here a little bit. I'm going to extend it out a little bit here. And over here, I'm going to bring one of the arc sections in a little bit. Now you can imagine if I did this over and over again, I could slowly, gradually make any shape I'd like by taking little pie slices, pushing them in, or pulling pie slices out, and basically getting a larger, so that the shape of the path looks like this. Right? Now, only these curved parts of the path would give you any value in the line integral. This part of the path wouldn't give you any value, because at this part of the path, the magnetic field would be perpendicular to the path everywhere, so it would be 0. Only these contributions, only the circular curved contributions would give you any value to the line integral. And it would be a line integral with a smaller radius, but that would just make r smaller here. So in every case, the radius r will cancel with the curvature of the loop. And regardless of the shape, you're always going to get mu naught times I. So it works. It's valid for any shape. Valid for any shape. Is there a question?
I was going to say, do you have to do like different integrals for the spot length of the radiuses?
Well, you'd have to. This would be one integral, one line integral, and your path is just a complicated path. So in calculus, this would be a piecewise integral. You'd have to break the line integral around the loop into a piecewise integral, and you have a bunch of different pieces, and you add the pieces up. So what I'm saying is these pieces actually equal 0, and it's those curved pieces which only give you anything. But the important result that we get from this is, regardless of what the shape is, as long as the path is closed, I get mu naught I. And that is, I'm going to put a circle here, again, to indicate it's a closed path. As long as the path is closed, regardless of the shape doesn't matter, I always get mu naught times I. Yes?
How are B and S parallel?
So B at this point is vertically downwards, and ds, which is tangent to the Amperian loop, ds also points downwards like that. So those two vectors at that point are pointing vertically downwards, so the angle between them is 0, so the cosine of 0 is 1. Now at this point, for instance, ds looks like this, and as I go around, my ds element is changing its direction depending on the direction, or depending on the curvature of the loop. Your little ds element is always tangent to your path. Yes?
Does that mean if the wire was pointing out, it would just be a negative in front? Or would it be the same?
A negative in front of where?
The mu naught I.
So in that case, good question. So we typically, to avoid these extra minus signs popping up, we just choose our path direction to be in the direction that the current is, that we expect the magnetic field to be moving. So if the current is in, choose your Amperian loop to go that way, right? That way your B dot ds is positive, because if B dot ds are anti-parallel, I have a cosine of pi, or 180 degrees, which is -1, and you just get a negative. But if you always choose them in the same direction, you get a positive number. So if the current was going out of the board, I would integrate around the other direction, and I would just get mu naught I. So the direction is important. You can always get positive if you just change the direction to match the symmetry of the field that you expect. Yes?
So how could you get, I'm sorry, how could you get ds perpendicular to B? If you just,
So on these elements right here, on the elements right here, for instance, if I was to look at the magnetic field at that point, well, the magnetic field at that point points this direction, but my line element points like that as I go on that element of the path. So when I take the dot product between B and ds, at that point, it's 90 degrees. The cosine of pi over 2 is what? 0. So I get, those contributions that doesn't give me any contribution to my line integral, because it's perpendicular everywhere. All right, now, so it's valid for any shape. And since it's valid for any shape, we can actually make an argument to say it's really valid for regardless of where the current passes through, because I could always morph the shape to make it look like a circle about that point with various pi sections of different radius. So I could say, all right, well, my current is actually complicated. It's actually, there's actually one here, you know, and there's two over here, right? And then there's a big chunk of current this way flowing out of the board. You know, I can have a bunch of different current inside that loop. So it's going to be true. You're always going to get mu naught I. It's going to be independent of where the current passes through. And it's also independent of how much current. So then we generalize all these statements together to write out Ampere's law, and Ampere's law basically just says the line integral around a closed loop of B dot ds equals mu naught I n closed. So this is Ampere's law. Enclosed current. So I enclosed is the amount of enclosed current through that loop. So your line integral only depends on how much current is penetrating through that Amperian loop. Yes?
If the line integral is only dependent on the current, then how can it be independent on how much current is there?
Oh, well, maybe a clearer way to write that is it depends only on total enclosed current. So if I have some current that's coming in, some that's going out, those contributions cancel each other out. It's basically the net amount of enclosed current that's flowing through the loop. So some could, basically one current, once I have a positive current this way, this way, and my Amperian loop is that direction, some's going to be positive, some's going to be negative, And those contributions cancel each other out to give you the net amount of enclosed current inside that loop. Just like in Gauss's law, you can have positive and negative charge inside a Gaussian surface. But the only thing that matters is the net amount of charge, the net enclosed charge inside that Gaussian surface. So the only thing that matters for Ampere's law is the net enclosed current. And you can have positive current or negative current, depending on which way the current is flowing with respect to the Amperian loop. All right, well, so we're going to end class today with one example of applying Ampere's law. Okay, so we've talked, and there's lots of examples that you can use Ampere's law for. As I mentioned, the best way to actually, what it's going to be useful for us for is to apply it to situations where there's a high degree of symmetry. There's a high degree of symmetry in your charge configuration, and that allows you to find the magnetic field of that current distribution in a simple way. So the example that we'll look at is a thick wire. I'm going to apply Ampere's law to a thick wire. Okay, let's say I have a uniform current moving through a thick wire, and I want to find the magnetic field inside and outside the wire. Find the inside and out. Well, we could use the Biot-Savart law to find the magnetic field inside and outside the wire. But you can imagine that integral would have to use the J d tau, the current density, and then it'd have to be a volume integral, so it'd be a triple integral, and have a cross product involved there. It'd be a very complicated integral to set up. So we're going to do this integral in a very simple way. It'll save us many, many steps just by using Ampere's law, that equation over there. So first of all, let's look at the region inside. Let's look at little r is less than big R, so we're inside the loop. And for that, what I'm going to do is I'm going to create an Amperian loop that's inside the wire. And I'm going to choose the orientation. So here's my Amperian loop. So I'm going to choose the orientation of the Amperian loop to match the direction I expect the field to go. Because inside the wire, if the current is going this way, I do expect the field to wrap around in this direction. Now, what kind of symmetry does this distribution of current have? It's highly symmetric, right? It's uniform. What kind of symmetry would you say it has? So raise your hand. Identify one of the symmetries of the current. Yes?
Axial,
What do you mean by axial?
like as you change degrees around, it's symmetrical.
Okay, so I could rotate, excellent, I could rotate the current about the central axis, and if you were wearing a blindfold before, and someone rotated it, took the blindfold off, did anything change? Well, it looks exactly the same. So the magnetic field can't depend on any angular coordinate. Very good. So there's a rotation symmetry about the central axis. Any other symmetries? We'll say it's a long wire. Yes.
Translational along the axis of the wire.
Excellent. So you could also tug the wire if it's a long wire, and you wouldn't know that it's moved a little bit this way or a little bit that way. So it also has translation symmetry. Now, it has actually one less symmetry than just a cylinder of charge, because a cylinder of charge, you could take it and you could flip it like that, it looks the same, but for a current, it doesn't match that symmetry because he did that, the current would be flowing the opposite direction. So all of this leads us to the conclusion that the magnetic field along the Amperian path, well, let's say we don't know anything about the field, just by argument of symmetry we know along this path, I'm going to say this path has radius little r, we know along this path the magnetic field is only going to point in the angular direction, but it has no angular dependence. It's only a function of r. So writing out Ampere's law, we would write the line integral of b, and b only can depend on how far you are away. It can't depend on any of the angular coordinates because of this rotation symmetry. And it's always parallel to the line element for the circle, so I'm integrating that, I'm multiplying that by ds. Right, now if my line integral is just a circle, b is actually constant. Right, so it can come outside because it's constant. And this is just equal to b as a function of r, the integral of ds. And this is just b as a function of r, 2 pi r. So we just did a line integral here. That's all we did. Line integral. Now I have to set that equal to mu naught I, and that's Ampere's law. So this equals Ampere's law says that this equals mu naught times I enclosed. Now let's find the amount of enclosed charge, the amount of enclosed current inside that loop. Well, the amount of enclosed current is going to depend on the current density. So J is going to be the current per unit area, pi capital R squared. That's your current density. It's uniform because the current is uniform. So your enclosed current is going to be mu naught times I enclosed. And I enclosed is just going to be J times A so let me write it this way, is I enclosed is equal to the double integral of J dot dA. Right? Current density is just charge per unit area dotted into the area element. But if the area element and J are parallel, what we get is the integral of J dA. And if J is constant, it comes outside of the integral, which it is for us. And then we just have the integral of J over that surface, so we just have J times A, the area of that loop. So if I just plug those numbers in, J is just equal to I over pi capital R squared, and the area of that loop is just pi little r squared. Pi's cancel out, and then we just combine, and we can write down our answer and solve for b. So we're just solving for b now by equating the line integral to mu naught I enclosed, and we have our answer. So let's just hold tight for another minute, and we'll just wrap this problem up. So solving for b, then, b is going to, what I have is b as a function of r times 2 pi little r equals mu naught I little r squared over big R squared. So b as a function of r, one of these r's cancels with one of them here. I get b as a function of r is just mu naught I over 2 pi r squared multiplied by little r. This is for R less than big R. What does the field look like when you're outside the wire? Well, it should look like what we already expect it to look like for a thin wire, mu naught I over 2 pi r. Let's just see whether or not that does hold out here. So if little r is bigger than capital R, what I have is, the line integral doesn't change, so I still have b of r 2 pi r. The only thing that changes is mu naught I enclosed. So j stays the same. The only thing that changes now with a larger area is the area of, when you're outside, is just the area of the current itself. So it would just be pi r squared multiplied by pi capital R squared, so just equal mu naught times I. So then B would be exactly what we would expect, mu naught I over 2 pi r. This is when R is greater than R. So plotting a graph, B as a function of R, it grows linearly until I reach the radius of the wire, and then it falls off like 1 over R outside the wire. And you can check if I put little r equal to big R, little r equal to big R, at the boundary conditions, those two equations match. So this looks very much like a sphere of charge, grows linearly, but outside it doesn't fall off as 1 over R squared, it falls off as 1 over R, because we're dealing with a long line of current in this case. Okay, so the last thing I have to talk about, which I'll do on Monday, but we've already kind of seen a little bit this week in lab, is the Lorentz force law. We'll talk a little bit that on Monday, but your homework then will be due on Wednesday for this chapter. And the rest of the week, next week, will be devoted to electromagnetic induction, which is the final chapter for this course. So Monday we're going to start.
Oh, I know.
We're going to start.
Also, there is
We're just going to talk really. Well, I'll start out class with just talking about this again. What we saw in lab. We'll start out talking about that, and then we'll jump right into Faraday's law.
5% today alone.
I'll do that. I'm going to basically 2 midterms taken together. Yeah.
And then we'll see LR circuit.
We likely won't get there to do LRC circuit.
What about inductors?
No.
Okay, so not that. So like just midway through chapter 30.
Yeah.
Okay, I'm just looking at.
Yeah, just to, because if you look at my notes, typically we don't have time to get to LRs or LRC circuits.
Okay.
Yeah.
So I don't need to worry about that or
No.
inductors.
Yeah, don't worry about
So like
that.
right up to before inductors.
Yeah.
Okay. Okay.
Just Faraday's law, essentially. Faraday's law and Lenz's law. You know, if you look at some of the practice finals.
I just want the answers with them so that I can know if I'm doing it right.
Yeah.
Okay. Thank you.
Here's your camera.
How did it work out there, John?
I think it looked all right.